Hello everyone, my name is Nimisha Sinha and today my friends and I will be presenting on multi-objective A star or MOA star. In this presentation, we will discuss the need for multi-objective A star, its algorithmic approach and how it works through an example. We will also explore improvements made to MOA star over the years and highlight a research gap that still exists in this domain. A star is one of the most widely used algorithms for state space search problem in artificial intelligence. It follows a best first approach, always expanding the node with the lowest cost function value denoted by Fn. Since A star is well-known algorithm, we will not dive deep into its working. Key properties of A star make it admissible, efficient, and capable of expanding only necessary nodes. However, these properties are based on single objective optimization. This means A star can only optimize for one objective at a time, which make it unsuitable for many real-world applications. In reality, most problems involve multiple objectives that need to be optimized simultaneously. For example, in transportation system, we need to minimize distance, time, and fuel consumption. Network routing, we optimize for cost, latency, reliability. Robotics, we aim to balance energy consumption, time, and safety. These scenarios cannot be efficiently solved by A star. So, limitation of A star is it assumes a single scalar cost function cannot handle multi-objective problem. Discard paths that may be non-dominating in multi-objective settings. A non-dominating solution is a solution where no other solution is strictly better in all objectives. Instead of single optimal path, multiple non-dominating paths may exist. One might think a simple way to deal with multiple objectives is by converting them into single objective function using weightage approach. However, this approach has significant drawbacks as it generalizes the importance of each objective and does not always provide the best solution. Hence, we need an algorithm that can directly handle multiple objectives without merging them into one. For example, we have two paths, path A, path B, which take 10 minutes and the risk factor involved is 8, and path B takes 15 minutes and risk factor involved is 3. A star will always pick only one path based on the based on time or risk factor. But when more than one objective are required, A star won't work fine and has to remove one possible solution. Here we can see both are non-dominating solutions. So we can choose A as well as B. This is where multi-objective A star or MO star come into play. Proposed by Barley S. Stewart, Chelsea C. White 3. MO star is one of the fundamental algorithms to tackle multi-objective optimization problem by finding all non-dominating solutions instead of just one. Here, concept of non-dominance is very important and is the backbone of MO star. Non-dominating solution is solution where no other solution is strictly better in all objectives. This solution are also known as Pareto front. Here we also discuss about how it differs from A star. A star select only one optimal path, whereas MO star finds all non-dominating paths. A star discard alternative paths, whereas MO star preserve non-dominating solutions. Now we have covered the basis of introduction of MO star. Let's move on to algorithm itself. To explain this in detail, I would like to invite Shivang Gupta to take over.
Thank you, Nimisa. Now, before diving into the algorithm, let's first understand some key concepts of MO star that will help us grasp its working better. In MO star, rather than having a single value of fn, we have a vector fn which contains all the values of different objectives. Also, rather than just finding one path like in A star, here we try to find all the paths and solutions that are non-dominated. For MO star algorithm, our inputs are directed graph, which can be implicit also. A start node S, set of goal nodes denoted by capital lambda, a set of cost and heuristic functions for each objective. And for output, we get set of all non-dominated paths from start node to any goal nodes. Now the first step is to initialize everything we will need for the search, which includes creating open list, closed list, as well as list to store solutions, which are solution cost, solution goals, and labels. We also add our starting node to the open list. After that, as long as the open list is not empty, we try to find possible paths to take from the open list. To do that, we find all the nodes in the open list which have non-dominated cost vectors, which is our Fn, and put them into a separate set called ND. Now, if the newly created ND is empty, which means that we have no solutions remaining. So we return all the solutions that we already have accumulated. Else, using domain-specific heuristic which helps us to choose a node n from ND to expand. Now we need this heuristic because in real-world scenarios, certain objectives might be more critical than others. For example, for our delivery example, we might want to prioritize cost over anything else. So this heuristic helps us to choose nodes which have less cost. Now we check if the node we just expanded is a solution. If it is a solution, then add it to the list of solutions and filter our open list by removing all the nodes that have their FN dominated by cost vector of currently found solution. And then repeat the whole process by going to step 6. Now, if our current node is not a goal node, then we expand it and find all of its children. These children can have two cases. Either they are new node, in which case we will just add it to the open list and create a back pointer from m to n in labels. But if children is already available in the open list, then we need to check if our current path is dominated by already existing path. If it is not dominated, then add to the open list. If this new vector dominates an already available node, we remove that old node and add a new one to the open list. Now, we repeat these steps until we find all the non-dominated solutions. Now, let's talk about memory consumption and complexity of MO star. Here, the memory uses will be very high as we need to store multiple solutions. Computation will also be slower as we check for all newly discovered paths. But this approach leads it to be complete. Now, MO star is designed such that if we have only one objective, it will totally act like normal A star algorithm. You can try this yourself. Here, you can see a comparison between A star and MO star. You might have a question, what is Pareto optimal? Pareto optimal means nothing but just a type of solution that is not dominated by any other solution, which can also be said as one of the best solutions. Also, time complexity of MO star, which is big O of n into m, where n is the number of explored nodes and m is the number of non-dominated paths, is also very simple to understand as we might need to explore n nodes for each non-dominated path, and we have m such paths, so complexity is n into m. That was quite a lot of information to take in. To make it more clearer, let's go through an example. Now, I would like to invite my friend Janil to walk us through it.
Thank you, Shivam, for detailed explanation. Now, let's go step by step with this example to better understand the algorithm. Now, in this example, we have a graph given. The graph is given to us, and here is a one start node and three goal nodes here. We have two objectives whose values are represented by this vector, where first value is for first objective, second value is for second objective. Now, in this example, we assume that the we assume that the heuristic value is equal to the next node's cost. So for s21, the heuristic value is 1 comma 2, s22 is 3 comma 1, and s23 is 1 comma 3. So here you can see in this table that node ns is in open, for its gn will be 0 and its fn will be 1 comma 2, 2 comma 3, cause fn is equal to gn plus hn, and here our gn is 0 comma 0. So fn will be equal to hn. This is a fairly simple assumption that we also made in A star. I guess you might not have any problems with this assumption. Now for the second iteration, if we explore S, then we have gn cost for 1 as 1 comma 2, for 2 3 comma 1, and for 3 is 1 comma 3. And from 1 we can explore two nodes, node 4 and node 5. From 2 we can explore two nodes again, 5 and 6. And from 3 as well we have two nodes, 1 comma 3 and 1 comma 2. It is 6. We can explore only one node from 3, which is 6. So now if we see and calculate heuristic cost for all three nodes, we will see that 1 and 2 have the non-dominant. For 2 it will be 3 comma 3, as you can compute, sorry, not 3 comma 3, it will be 5 comma 2, and for 3 it will be 2 comma 5. For 1 it will be 3 comma 3 and 2 comma 4. Here we can see that uh, here we can see that 2 comma 4 dominates over 2 comma 5, and 3 comma 3 is also non-dominant. So 1 is a node which is not dominated by any of these node. So we will explore 1. 2 is also non-dominated, but as Shivank has discussed that in this cases of tie, we try to optimize for some value which is our heuristic, which will be done by a heuristic. So assume that here we have some heuristic which prioritizes 1. So if we explore 1, then 1 has two childs, 4 and 5, which will be explored. So if we explore here, you can see 4, 5, 2 and 3 will be in our open list. Gn value will be same for these two, 3 comma 1, 1 comma 3, and hn value will be also same cause there is no change in their hn. For 4 comma 5 it will be 3 comma 3, and for 5 it will be 2 comma 4. Now, if we explore HN values for 4 and 5. For 4, it is 3 comma 3 plus 5 comma 7, which will be 8 comma 10. And from 5, we have two options, from go to 7 or go to 8. For 7, it is 1 comma 3. So 2 comma 4 plus 1 comma 3, it will be 3 comma 7. And for 1, it will be 3 comma 5. So 5 has a heuristic cost of 3 comma 5. This has 8 comma 10. So still our heuristic cost here of 2, which was previously, as we calculated, 5 comma 2 and 2 comma 5. So 5 comma 2 and 2 comma 5, all of these still 5 comma 2 and 2 comma 5 still dominate over any of these costs. So we will choose one of these nodes here. Again, using heuristic, we will choose 3, and we will explore 3, which is shown by this double asterisk. Now if we explore 3, 3 has only one child, which is 6. So for 6, 6 will be added to the, and 3 will be moved to the closed list. As you can see here, 3 is moved to the closed list and 6 is added. 2, 4 and 5 has their values not changed, so we are not showing them. Also one concept that I forgot, labels. This labels concept is that from which node this value came. So for 5, if we go through 1, that's how using cost 2 comma 4 we reached 5. You will see in future that this label can also be changed. So for 2, 5 and 6, here we see that 5 comma 2 is not dominated by anyone. So 5 comma 2, for 4 it was 8 comma 10, for 5 it was 3 comma 5, and for 6 7 comma 7, and 4 comma 9. So 5 comma 2 still reigns supreme, so we will explore 5 comma 2. Now, sorry, we will explore node 2, which has the fn value 5 comma 2. If we explore 2, 2 has two possibilities, 5 and 6. Now from here we will see that 5 is already in the open list. 5 is already in the open list. So which value we should keep and which value should we discard? For that, as you remember, and Shivang told in the algorithm, in this type of cases we will check which dominates over which. So for here, if we see that for 5, its heuristic value is coming as 3 comma 5, 3 comma 5. But now if we go from 2, it is 3 comma 1, 2 comma 1. So 5 comma 2 plus 1 comma 1, it is 6 comma 3. So 6 comma 3 is using this value 2. So 6 comma 3 will be added because it is not dominated by any value of existing 5. So 6 comma 3 will be added. So as you can see, 3 comma 5 and 6 comma 3 is also added. For 6 similarly, we have 4 comma 9 and 7 comma 6, which replaced 7 comma 7. This is going from 2. This is going from 2. This is going from 3. This is going from 3. And we have similarly added back pointers in labels using these nodes. Uh, if we continue this exploration, here 3 comma 5 is not dominated by anyone, so we will explore node 5. Now using node 5, we can see that if we explore node 5, we explore 8, 7. So in our open list it will be 4, 7, 8 and 6. Now out of these values, the most dominant over will be 6. uh, 8 and 6 both have non-dominant strategy, but as we have told, we have some heuristic which prefers 8 over 6, sorry, 6 over 8. So we will explore 6, and after exploration of 6 we have 8, 9. So value of 8 will be updated or not accordingly, as we have told, depending upon the depending upon whether its heuristic value is it is functional value is dominated by anyone. uh, Now here we see that new value of 8 is added, where it is the actual value of 8 is 3 comma 5 6 comma 3, now 6 comma 7 9 comma 5, sorry. And this exploring 6 does not add any dominance of any non-dominated fn value, so it will stay as it is. Now now our heuristic prior, we have 8 and 7 which are non-dominated, and we will choose 8 from here. Now, if we choose 8, 8 is connected with two solutions. So these two solutions will be added to our open list. Now, as you remember in the algorithm, we will check if we have any, if we have check, we check if we have any solutions that are non-nominated by any other solution. So we have gamma, which is gamma 3, which is not dominated by any solution because there are no solutions, and gamma 2 is dominated by gamma 3. Here 6 comma 7 dominates 8 comma 12, so it will not be explored, but gamma 3 will be explored, and after exploring gamma 3 it will be added to solution cost, it will be added to close as well. So we can see that gamma 3 6 comma 7 9 comma 5 is added. Now as long as gamma 3 exists, gamma 2 can't be a solution, cause gamma 2 is a suboptimal solution compared to gamma 3. As we have discussed in the algorithm, gamma 3 is a non-dominant solution, but gamma 2 is dominated by gamma 3's 6 comma 7 value, so gamma 2 will be not explored, but we still have a non-dominated node 7, so 7 will be explored. And if we explore 7, we will reach gamma 1 and gamma 2 both. Gamma 2's value will also be updated or not, let's see. Gamma 2's value is not updated, only gamma 1 is added, and gamma 1 has one hn value which is non-dominated, which is 4 comma 11. For yeah, also for solution, fn will be equal to gn, cause we have reached the solution, so hn will be equal to 0 for all of the vector nodes. So hn will be 0 and fn will be equal to gn. Now as you can see, we will add gamma 1 as gamma 1 is a solution. We will add gamma 1 and we will explore it first. So gamma 1 and gamma 3 will be our final solutions, and gamma 2 will not be explored, and there are no solutions left, so 4 9 and gamma 2 will be removed, and our solution will be done. I guess this example helps you to understand the algorithm more. Now to talk about the some real life examples of this MOS algorithm, also some improvements made on it over the years, and some research gap that still exists in this space. I would like to invite my friend Aditya.
Thank you, Janil, for helping us understand it better. Now, before diving into improvements, let's see a real life scenarios as an example. For this problem, we want a robot to navigate from the start to the end of a warehouse, but we want the robot to minimize its time as well as the battery uses, and it should also avoid obstacles. In this example, MOStar will find multiple optimal paths and can use a heuristics that prioritizes one objective over another, depending on the current state. For example, if it is running on a low battery, then it might try to optimize for the battery. Additionally, in a real life scenarios, the environment might changes over the time. For example, there might be some obstacles in its regular path, so it can adapt to that as well. So here I gave some other real life examples and their objectives we might want to optimize the problem for, like traffic navigation, video games, disaster response, logistics, healthcare, and etc. So now MOStar is a great algorithm, but it has its own fair share of issues. Some of which are that MOStar expands all of the nodes when some of them are even unnecessary. Also, when a new non-opinionated path is found, it opens all the nodes. It also has other issues such as storing unnecessary non-dominated paths and redundant paths. Additionally, heuristics are not effective in reducing the number of expanded nodes, all of which leads to a high net memory uses. So to deal with this, Almando and J.L. Perez da la Cruz proposed an alternative approach to MOStars. In this approach, called New Approach to MOStar. So we expand individual paths and maintain a search graph rather than exploring all the paths reaching a node simultaneously. So a key difference in a new approach to MOStar is that it maintains a graph instead of a tree, but otherwise it's similar to MOStar only. Using a graph helps maintain back markers effectively and allows exploration of individual paths. Here is a basic comparison between a MO stars and new approach to MO star. Here we can see that new approach to MO star is a very helpful in reducing the memory uses of MO star by using different methods such as a memory overhead and less effective heuristic uses, solution storage issues, etc. So now new approach to MO star is a good, but there is still exists some research gap in the domain of a multiple objective search. We will now discuss some of the points over it. One of the major challenges with the MO star and new approach to MO star is handling the larger scale graphs, such as a road networks or complex robotic planning environments with the millions of nodes. As the number of nodes grows, the size of a open list and the number of dominance checks increases significantly. It leads to the high memory uses and slow performance. One approach to solving this to implement we can lazy evaluation strategy where we only expand the nodes where absolutely necessary. Another promising direction is parallel computing, which distributes the search process across multiple processors to handle large scale pathfinding more efficiently. So both MOA star and a new approach to MOA star assume a static graph, meaning they don't adapt well when the environment changes. For example, in a real life traffic navigation or robotics, road conditions, obstacles, or a cost may change dynamically. One way to improve this is by developing an incremental version of a new approach to MO star, which updates only the affected part of a search graph instead of a recomputing the entire solution. Another approach is to use reinforcement learning based heuristics, allowing the algorithm to adapt dynamically to changes in a real life scenarios. Now, new approach to emotional lacks an effective way to balance exploration, searching broadly for all possible solutions, and exploitation, focusing early on a most promising solution. This can lead to two issues: expanding too many unnecessary paths or terminating early before finding the best trade-offs. A possible improvement is to introduce adaptive heuristics that dynamically adjust the search strategy based on the progress. Another method is to explore Monte Carlo tree search, which is widely used in AI decision making and can help balance search effort across different Pareto optimal paths. To wrap up, today we explored multiple objective A star algorithm and its challenges and its advancements. So particularly Namo star, and we saw how MO star helps solve the problems with multiple objectives, but also how its computational and memory demands have led to a ongoing research and improvements. That concludes our presentation. We hope you find it insightful. Thank you.